Okay, so what's the math that goes with this? It's in your lab manual, but let's go over it again. This is your wheel. This tag will start the photogate timer. This one will stop it. So you're measuring the time it takes from the tap to go from here to there. That's half the circumference of the wheel. You're going to list it in terms of 3 decimal places because this photogate system is accurate to that much. Your hanging mass is going to be 0.5 kilograms. Your outer radius is what we measured in your initial estimate right here when we are measuring the wheel's outer rim. So your tangential acceleration would be 2 times your effective length, which is half the circumference of a circle, divided by the time under acceleration squared. We're assuming, of course, that we have no initial velocity to mess up our data with, like misplacing the photogate could cause that. Then sum of the forces in the y direction would equal the weight minus tension. That would equal the mass times the tangential acceleration. Rearranging that, tension would be equal to the mass times the quantity, gravity minus the tangential acceleration. Now we can put this into the torque equation, and the torque would be R0, the outer radius, times that tension. That would equal the rotational inertia times the angular acceleration. But that angular acceleration is merely the tangential acceleration divided by that outer radius. If we do about 5 steps of algebra, we're going to get the rotational inertia is equal to m times the outer radius squared times the quantity, gravity over the tangential acceleration minus 1. So you're going to do this 10 times, and then you're going to average out your rotational inertias. They should be within an order of magnitude of the estimated value. If they're all close and they all agree, great, everything's perfect. But in life, nothing's ever perfect. There could be friction in the system, you could have misaligned the photogate. A number of things could invalidate this data.